Hi students, welcome back to yet another session on electrostatics. In the previous classes you have learned Coulomb's law, the expression for force, field, etc. due to a single charge and due to multiple charges. Today we are going to learn how to represent electric field in a region. So how to visualize an electric field in a region. So for that we are going to study about electric field lines. So electric field lines is a way of visualizing how the electric field is in a region. This was in the beginning explained by Michael Faraday himself. Electric field lines are imaginary lines. They are imaginary lines drawn in a field to represent the nature of the field, the direction of the field, strength of the field, etc. So it's a way of visualization, that's all. So if you have a positive charge, if you take a positive charge, how the field will be around this charge, let us just check that. You know, if I place a unit positive charge here, a test charge, then that is repelled by the charge present here. So you can say the field is in that direction. So this is a vector which shows the strength of the field and the direction of the field. In the same way, if I place this test charge somewhere here, once again the charge is repelled, but the force of repulsion is less now. That is, length of the vector I have just reduced. So strength of the field goes on reducing as you go away from the given charge. You know that. So in this manner, if I place a test charge somewhere here, of course the force will be in this direction. Now if I place a test charge somewhere here, in that direction, but of course the magnitude is going on decreasing. So as you go away and away, the magnitude of the force or field decreases, whereas in the nearby, as you come close and close, the magnitude increases. So vector is longer as when you are closer to the charge, and it is shorter when you are away from the charge. In this manner. So these, if you just join all these points, of course, if I just draw here one more vector, longer vector I have to take. Any unit charge, if you place it at any point, will show the direction of the force acting on it. Anyways, now if you join all these points, then that becomes the electric field line. So in this manner. So these are electric field lines around the charge. So in short, what we do is we just represent the field lines as continuous lines or curves. So for a positive charge, the field lines are in this manner. Now, you may be thinking, how many lines should I draw here? Of course, you can draw infinite number of lines. So, some students may draw this many lines, some students may draw some more in this manner, in between also. So, there is no end to it. You can just go on drawing number of field lines. You can understand yourself. You can just go on drawing number of field lines in between also. So, infinite number of lines can be drawn. So, this is the field pattern of a positive charge. Now, what will be the field due to a negative charge? So, negative charge will have similar pattern, only the difference is the electric field lines are opposite in direction. That is, if you place a test charge somewhere here, it will come towards the negative charge. So, you know that. So, therefore, the field lines are exactly opposite compared to that of positive charge. This is the field pattern of a negative charge. Of course, I will not draw more lines, so this is very sufficient actually. If you want, you can draw as many you want actually, infinite number of lines you can draw. Then, what represents the, of course, direction you understood. So, what represents the strength of the field here? Strength of the field is represented by the density of field lines, we can say. That is, if you look at this region here, in this region, the field lines are say 1, 2, 3, 4 lines are there. Now, same volume, if I just consider somewhere here, field lines are only 2. So, as you go away and away, you find the density of field lines goes on decreasing. So, where the density is more, strength is more. Where density is less, strength is less, we can say. Means, where the field lines are crowded, the strength of the field is more. And where the field lines are spread away, the strength is less. But then you may be thinking, what if like a student has drawn more number of lines maybe, or another student has drawn less number of lines, then how do you get the density strength of the field? Very simple. You draw as many lines you want. You can see that closer to the charge, density is more. Away from this charge, density is less. Even if you draw one more field line also in between, it is going to increase here as well as here. Thereby, automatically you will find that close to the charge here, density remains more, irrespective of how many lines you draw. So it is not the number of field lines which matter, it is the number of field lines passing through an unit area which matters. If you consider a unit area perpendicular to the field lines, here or here or here like that, in whichever place you find more number of field lines are passing through the unit area, normal to it, then there the field will be stronger, we can say. So that is electric field lines. So what are electric field lines basically? Electric field lines are imaginary lines drawn in electric field along which a test charge would move. We can say like that. So if you place a test charge here, it will move in the direction of this field line. So electric field line is an imaginary line along which a test charge tends to move. Now what are electric field lines represent? Give. So electric field lines can tell you the direction of the field as well as strength of the field. Now there are some characteristics of field lines, we will come to that. Now before going to the characteristics, let us try and understand what happens if you have different setup of charges. Say for positive charge you understood. How will the field pattern be for a combination of charge? For negative charge it is like that, you understood that also. So for a combination of charge, say there is one positive charge here and there is a negative charge here. Now what will be the field pattern in this case? Now you can understand, if you place a test charge somewhere here, it is repelled by positive and attracted by negative. So anywhere in between, you will find that the test charge will tend to move from positive to negative. So whereas if you place the test charge here, it is attracted by negative. Therefore, it is towards negative. So if you place the test charge somewhere this side, it is repelled by positive. Therefore, it is away from positive. Now if you place the test charge somewhere here, of course it is attracted, here attracted, somewhere here repelled, here repelled. Whereas what if the charge is somewhere here? If the test charge is here, it is repelled by positive but attracted by negative. So you will find that it is repelled from positive and moves towards negative. Here also same. The test charge is repelled by positive but attracted by negative. So this is the field pattern due to a combination of positive and a negative charge. If you have 2 point charges, positive and negative, separated by distance, you will find a field pattern in this manner around them. This combination positive and negative can be called as an electric dipole. There are 2 poles, positive pole and a negative pole. This is an electric dipole. You are going to study and understand more about electric dipoles later. Now, so for an electric dipole like this is the field pattern. Now from this you can understand all the field lines, they originated from positive, they terminated at negative. So electric field lines start from positive, end at negative. This is one of the very important characteristics of electric field lines. And one more thing you must have noticed here, no 2 electric field lines are crossing each other. I will come to that point again, 1 second later. Now let me just take another setup where we have 2 identical charges, means like charges, say both positive. If you have both positive charges, then of course if the unit charge is kept here, some test charge kept here, it is repelled away. That side also it is repelled away like that. Okay, so this is clear. Repelled like that almost. Whereas if I place a test charge somewhere here between the 2 charges, then it is repelled by this charge, so it tends to move like that, but it is repelled from the other charge also. Therefore, it is going to slip away either upward or downward, away from the axis between the 2 charges. So it will go like that. It may go like this. So in this manner, the field lines will be. Now, what is this region here? This is a dead point, a null point, where there is no field, we can say, there is no force at exact center between the two charges. That is, if you place a test charge exact center between these two identical positive charges, then that charge will not experience any force, because this left hand side charge is trying to push it towards right, whereas the right hand side charge is trying to push it towards left with equal and opposite forces, because they are equidistant and they are identical charges we have taken. So therefore, there is a null point here. Now you may be thinking, what if these two charges are not identical? If these two charges are not identical, you may find this null point shifting slightly this way or that way, that's all. But there will be a null point most of the times. So in most of the cases. Of course, we are going to understand more about such cases later. Now, for a pair of charges which are like charges, like positive each, the pattern is like this. Then what will it be if the two charges are negative? Simple. The pattern will be exactly same. Only difference is all the vectors are inward, towards. So all these vector symbols, so the directions you have to change, opposite, exactly. So that will be the field pattern of a combination of charges. So for a dipole, means unlike charges, the field pattern is in this manner. For a pair of charges which are like each other, so which are identical, the pattern is something like this. Either arrows towards or away based on whether they are negative charges or positive charges. So that is about field lines. Then let me just mention in brief the characteristics of field lines. Definition is: electric field line is an imaginary line drawn in an electric field along which a test charge tends to move. Simple. What all electric field lines can give you? Direction of the field they can give at any point, and also strength of the field. And what represents the direction? Of course, the arrow. And what represents the strength of the field? That is the density of field lines. That is number of field lines passing through an unit area at that point, perpendicularly. So in this manner, basic idea you got. Now, what are the important characteristics of field lines here? So first thing, electric field lines always, start from positive, end at negative, and they do not cross each other. What happens if they cross each other? If they intersect each other, if you have two field lines which are going in this manner. This is impossible, because what is an electric field line? It is a direction, it is a path along which a test charge tends to move. If you place a test charge here, say it is moving like that, it comes to the junction here, then which side will it move? It has two directions to move, that is upset. It can't move in two directions at any instant, correct? At any point of time, it can't just move in two directions. So same way, if you place a test charge here, that also comes like this and comes to the junction and it has two ways to move ahead. So that is impossible. So therefore, no two lines of force or lines of electric field lines, it's the same thing. Okay, electric force lines or field lines, both the same, doesn't matter. So no two lines of force or field can intersect each other. That is another important characteristic. Means first, always the electric field lines started positive and ended negative, and they never cross each other. Then in these pictures which I showed you, you can see that electric field lines never form closed loops. It is not like the field line starting from here again coming back to that same point. No, it is impossible. It is impossible to have a closed loop like this. Closed loop may not be a circle only, it can be any path. So it can't be closed. Means field lines cannot start from a point and end at the same point again. Why? Because the point which we are talking about, so when you place a test charge there, it is supposed to move. So once the point charge moves there, again why will it come back to the same point? First of all, why will a charge move? Because a force acts on it there at that point. It will not come back to the same point again, because there is already a force it can experience there, right? So it can't have a closed loop. Whereas this is in accordance with conservation of field, which you are going to understand in the coming topics. Anyways, so just remember here that electric field lines do not form closed loops. That is impossible. Then electric field lines in this manner, they are continuous curves. They can be continuous curves without breaks. They are break-free curves if the region doesn't have different charges, other charges. That is, in a charge-free region, electric field lines are continuous curves. So these are the few characteristics, important characteristics of electric field lines. Now let me just tell you very important kind of electric field which we will be seeing very often in the discussions. That is called uniform electric field. Uniform means it has to have same strength at every point. Strength of the field is same and it has a common direction at every point, of course. So this is represented by number of equidistant parallel lines. So uniform electric field, it is represented by number of parallel equidistant field lines. So as they are equidistant, so line density through any unit area normal to it will be constant at every point here, and also it has common direction. That's an uniform electric field. So strength is same at every point and also the direction is same. This is uniform field, and most often we will be using this kind of electrical field for all our different concepts to understand, because this is the easiest situation. Whereas you can have irregular field lines, if not equidistant, there are different kind of curves, of course. So that will be a complicated field pattern where the strength is not same at every point, it keeps changing at different points. So then understanding different situations will be difficult. So we are going to use most of the times only uniform field. If it is a rightward field, it is like this. Of course, if you have upward electric field, all the arrows turned upward or downward or leftward, of course. Whereas if you have if the field lines into the board, that is away from you, that is towards the board, then in that case we will represent with number of cross marks. So if you have cross marks, so that says the field is into the board. This is inward, into the board. Whereas away from the board, just dots. This is easy to understand. Just think of an arrow. So electric field line is an arrow, right? We represent electric field line with as an arrow. So if the arrow, bow and arrow, you know, right? An arrow you have seen. So if you just look at an arrow which is going away from you, the back end of the arrow you see, which is almost like a cross mark. Whereas an arrow coming towards you, that looks like a sharp edge, that's a dot. So this is all the arrows coming towards you. That is, electric field lines are away from the board towards you. Whereas here electric field lines are away from you towards the board. Right? That is into the board, out of the board. That is perpendicular to the board. These two cases we can have. So this is how electric field and magnetic field, electric fields are represented. So this is single arrow into the board. This is out of the board. That's it. That's about electric field lines. Thank you.